great pleasure to introduce the distinguished lecture series speaker, Professor Thomas Liggett, who is now the emeritus professor at UCLA. Tom did his PhD in 1969 in Stanford under Sam Carling. And then he moved to UCLA and then spent his whole mathematical life there. He retired a year ago, and he is famous for his 3 books, especially the one which is on interactive life.
There are 2 of them.
Okay, so
Especially
that one is especially Thomas.
Thank you very much. This is the first talk I've given, I guess, since my laptop died. And so I no longer have a laptop, so I'm glad that he had to provide the computer for the talk. I don't have the talk to provide the computer. So it's nice to be here. I've been posted here in Los Angeles for many years, since 1969. And but this is my first visit to this campus, I guess to the city, in all these years. So it's nice to be here finally. So what I want to do today is to tell you the story of the resolution of a conjecture. So this conjecture was posed slightly over 20 years ago by David Albus, who's in the statistics department at Berkeley, and took essentially all that 20-year period to be solved. Many people worked on it, got partial results, and I'll try to explain the problem and the partial results, the motivation for the conjecture, and so on. The way I learned about this conjecture was in the mid-90s. I was a member of the Board of Trustees at MSRI at Berkeley, and I had to go up for a board meeting. And so I called David up and said, you have time to talk that day after the board meeting. He said, no, I'm very busy, but I'll pick you up at the Oakland airport and drive you to MSRI, and then we'll talk in the car. So when I got to the airport, he opened the door, he said, hi, and said, I've got this great problem. So that's what I'm talking about today, this great problem. So I went home to Los Angeles, and I agreed it was a great problem, worked on it, couldn't make any progress. A few years later, I had a very smart postdoc from Cambridge, Alan Stacey, for 2 years, and we were looking for something to work on, so I said, how about the Alice conjecture? And that was very exciting, so we worked on it, no progress. Not so good for a postdoc, no progress. A few years after that, a former student of mine, Shireen Hajani, was looking for a problem. I said, well, this is a hard problem, but how about the Ellis conjecture? And she actually went home to her husband, who's also a mathematician, and they went together. His training is in topology, and between the 2 of them, they solved a very important special case. So the conjectures you see, we'll see, has to do with a graph, general finite graph, and they proved the full conjecture. In the case of the graph, is a tree, so it has no cycles. And there's certain things, you might guess, of a tree that makes it easier, it doesn't make it trivial. So they proved that special case. I had decided the whole problem was impossible. I've never solved it in my lifetime. But then about 3 years ago, we had a postdoc from Germany, Thomas Liggett-Apr, for 3 years, and a visitor from Rome, Pietro Caputo, for a year. And I was leading a graduate student seminar, graduate students talking, we criticize, and Pietro and Thomas were attending also. And at the end of one of the sessions, I happened to bring this up. That's something to chat about. And it turned out Pietro had worked on it before, and he couldn't get anywhere. And Thomas had never heard of it. But they were all excited. They were very young, much younger than I am, and they were so excited. I said, look, it's a very hard problem. I'm not going to solve it. I said, no, we want to work on it. So I didn't want to dampen their enthusiasm too much. So I said, okay, we'll work on it. And in 3 months we solved it. And one of the things that I like about this is that there are various kinds of collaborations in the world of mathematics. In this case, I would say that no 2 of us could have done it. It was just the fact that all 3 of us happened to be in the same place at the same time, with the same interests, but different ways of looking at mathematics, different ideas of how to pursue things, and it just all gelled over 3 months. Now this problem has to do with Markov chains. I could give, I was telling my host here, I could give the whole talk without ever mentioning probability. It has to do with matrices and eigenvalues, things that everybody knows about. But it's a bad idea to remove probability from contexts that are essentially probabilistic. So I'm not going to remove probability. So this has to do with Markov chains. Some of you know a lot about Markov chains, maybe some of you don't know anything about them. I'm going to give you a very brief description of what you learned in the undergraduate course on Markov chains. So what's a Markov chain? You have some finite or countable set. You have a point moving around at random. So what does it do? There's some parameters, these q, x, y's that you see on the board. And what happens is if the walker is sitting in a particular vertex in this graph, let's think of this graph, particular vertex, then for each edge that comes out of that vertex, there's a random time, which is exponential, with a parameter that's given by these numbers, q, x, y. And so you think of these as alarm clocks for each of the edges. Each edge has an alarm clock. And when the first alarm clock goes off, the guy moves, and he moves to the place that corresponds to which one ran. And he keeps moving around like this. That's a general continuous time Markov chain. So that's all described in this. Let's get the very use the ticker here. Does it work? No, I think so. So there are these numbers q of x, y, which give you what we call the rates of moving in various directions, moving across edges in this graph. And you can think of the rates analytically as the derivatives of the transition probabilities. So pt of xy here is the probability that if the chain starts at x, at time t will be at y. That's what it describes everything about the chain. And you differentiate it, set t equal to 0, you get these q's. Now the q's that I described before were all non-negative. Q of xy, where x and y are different. You can differentiate this even when x is equal to y. And notice that because the sum of the transition probabilities on y is 1, the sum of the derivatives is 0. So this matrix Q has off-diagonal terms that are all non-negative, diagonal terms that are negative, and they have the property that the row sums are 0. Okay? So that's the basic thing that describes the motion of the Markov chain. The fact that the row sums are 0 says that the matrix Q applied to the vector 1 is 0. So 0 is an eigenvalue, with eigenvector 1 on the right. And if the Markov chain is irreducible, which simply means it's possible to go from any place in the state space to the other place in some number of steps, then it's a simple eigenvalue. And then the other eigenvalues, we'll talk about in a few minutes, but the fact that 0 is a eigenvalue with an eigenvector on the right means there's also an eigenvector on the left. And if you normalize it properly, that's a probability distribution on the set of vertices. That's called the stationary distribution. And the fundamental theorem that you proved in an undergraduate course in Markov chains is this one listed at the bottom, that if you start anywhere, any x, and ask what's the probability you're at y at time t, and then t go to infinity, the answer is the stationary distribution of y. So the sigma y is a very important object. Now, Markov chains are used in modeling all over the place, but here are some p words that many of you probably heard about. Markov chain Monte Carlo, Gibbs sampler, and let me tell you just the basic idea that comes up in these applications. I said here, I think, how many hits I got for these terms on MathSciNet, and you see it's something that comes up a lot, and that's just the mathematics literature. If you look at the applied literature, and more hits. And so the idea is we have the following. We have a very large finite set, maybe Avogadro's number, or something like that. And you have some probability distribution of this very large set. And you want to choose a point at random and point out that distribution. Well, the set is so large, or the probability of any given point is so small, you just can't do that. So what people do is to set up a Markov chain with that Avogadro's number of states and rates that you can write down explicitly, and they will typically symmetrize the Q matrix. Notice if you look at the symmetry statement here, if you take the sum on y on the left side, you get 0, because the row sums being 0 in Q. And if you take the sum on y on the right-hand side, you get the statement that sigma is the stationary distribution. So anytime you have a sigma, and you can find Q's that symmetrize it this way, you have a Markov chain with that desired measure as the stationary distribution. And so what the people do in applications is they say, okay, I can't choose something according to sigma, so let me write down this chain, let me run it for a long time. Well, then the distribution is close to its limit. Use that instead of the original sigma. Problem is, how long should you run it? You can imagine with a very large state space, that's not exactly clear. So, in the talk today, all my Q's will be symmetric. And that means that sigma will be uniform. So sigma of any given x is 1 over n. And minus q now is this very special kind of matrix with non-negative off-diagonal terms, and rho sub is equal to 0 and symmetric. So it has a full set of eigenvalues, which I've written down. So 0 is simple eigenvalue, and then you have these others. And this smallest positive eigenvalue determines the rate of convergence. So this tells you essentially how long you have to run the chain before you're close to the loop. And here's a little formula, pt of xy is 1 over n, that's the limit, as t goes to infinity, plus something that's exponential in t, especially small in t, with the parameter lambda 1 appearing there. So basically you have to run it 1 over lambda 1 times to get reasonably close to the equilibrium. So this number, lambda 1, is a very important characteristic. This smallest positive eigenvalue is a very important characteristic that determines the rate of convergence of the equilibrium. Feel free to ask questions about it. I'll proceed. Now, you all know about variational principles, I think. The smallest positive eigenvalue is the largest value of lambda that satisfies this inequality for all functions that are orthogonal to 1. 1 because that's the eigenvector corresponding to the eigenvalue 0. So there's this variational characterization that comes up in a very important way in the discussion. So now I'm going to describe some specific Markov chains. So here's what's called a stirring process. So you have a graph. It has vertices, has edges, and with each edge you associate, first of all, there's a parameter c sub e, a negative parameter, and then what's called the Poisson process, which is basically so let me describe what it is. You take a given edge, and you have these exponential times that I mentioned before. And then the clock rings, and you start a new one. The clock rings again, you start a new one. The clock rings again, and so on. That's a Poisson process. So the times between rings are just independent, identically distributed random variables, exponential with parameter with base. So you have, at each edge, you have these Poisson processes going off. And you take the vertices of the graph and put labels on them. What I mean by labels will be clearer in just a minute. But whatever they are, the process evolves in the following way. You have these labels on various vertices. If you take an edge and the clock rings, you interchange the labels and the two vertices that are connected by that edge. Okay? Now you have a lot of flexibility in what you mean by labels and so on. So let's see what I mean by that. So here are 3 examples. There's my graph. In the top picture, I have one particle moving on the graph. That's that black thing. That's the label. So I have one label is this black thing. And so what does it do? Anytime the Poisson process rings on an edge that's not connected to the black one, nothing happens. You interchange empty and empty, and you get the same thing. But if you interchange the black one with the neighboring white, then you can think of the black particles moving. So this black particle is moving around on the graph according to one of these Markov chains. It's just an ordinary Markov chain, symmetric Markov chain on the graph, on the vertices of the graph. Well, you do other things. You can take a process that's called symmetric exclusion. The book that Vlad mentioned in the introduction has a whole chapter on the exclusion process and a big section on symmetric ones. So this is the only connection between my talk today and my usual work. So you can put black spots, you can think of 3 identical particles moving on the graph. So what happens? If one of these Poisson processes associated with an edge goes off, if the edge connects 2 black circles, nothing happens. If it connects 2 white circles, nothing happens. If it connects a black and a white, they switch. So you can think of this as, in this case, 3 particles moving around according to the 1 particle rule. But with exclusion, which means if a particle tries to move to an occupied site, he's not allowed to. Right? That's why it's called the symmetric exclusion process. Symmetric just means that the graph is undirected, so the rates are the same, doesn't matter which way you're going across the edge. And now we come to the extreme case where we put a different kind of particle at every site, at every vertex. Those are these colors. Now, an arrangement of colors like this is a permutation of these 6 vertices. And what happens when you apply this Poisson process at a given edge, you switch these 2 colors, what that means is that you applied a transposition to this permutation. So what you're doing is taking a Markov chain whose state space is the set of all permutations, some set, and you at random times applying this transposition. So as an example, to keep things concrete if you want, because the most famous thing of this sort is card shuffling. So there's a deck, so 52 cards. There are many ways to shuffle the deck. And one way, the one that's described here, is you take your deck, you at random times choose 2 locations of the deck, and at that time you switch it. You keep doing this, right? And the problem is how rapidly do you get close to being a completely shuffled deck. And what the one particle motion corresponds to then is saying, let's follow the location of the ace of spades. Forget the other colors, just where's the ace of spades go as we do this. And this says what happens to any subset of cards, not caring which, not identifying the cards separately. And this says what's happening to the full order permutation of the cards in the deck. Now, and I've ordered it this way because there's a clear inequality. You can think of this one as being a projection of this one. We take this process and follow the yellow line, the yellow circle, if it is like that. If you take 3 colors down here and just think of them being the same, they follow this. Okay? So I have these different Markov chains I can talk about. So now we're going to take the complete graph. Now why am I allowed to take the complete graph? That's the most general case. If I want to have a non-complete graph, missing some edges, I just set the C's to be 0 for the things. So I might as well, since the C's are general, I might as well take the complete graph. So we do that. So the one particle Markov chain, one up at the top of the previous slide, then has the Q matrix, Q of xy being Cxy, for 2 vertices x and y. While the Markov chain of permutations has Q of pi of xy. Pi of xy is the permutation you get by applying the transposition xy. So Q of pi of xy is Cxy. So here you have, the graph has n vertices. So you have one chain with n states and one chain with n factorial states. As you know, n factorial is a lot bigger than that. So each one has a set of eigenvalues. So I'm going to denote the ones for the, I'll call it the small chain, the one with n states. And I'll use the lambdas to denote those eigenvalues. And the large chain, the one with n factorial states, put a star. Eigenvalues for that chain. So the first observation, what I want to do is to figure out, remember lambda 1 is the key quantity. Now I want to know how lambda 1 and lambda 1 star are related. So first observation is that every eigenvalue for the small chain is an eigenvalue for the big chain. That's really because if you take the big chain and follow just one color, it's doing this, the small chain. And so you can take an eigenvector for some eigenvalue for the small chain and build up an eigenvector for the big chain, and we have described up here. And you get that to be an eigenvector for the big chain with the same eigenvalue. So all the eigenvalues for the small chain are eigenvalues for the big one. And in fact, the same kind of argument shows that any sum of this form, you take any finite set, any subset of eigenvalues for the small chain, add them up, that's an eigenvalue for the big chain. Now, how many eigenvalues for the big chain have we identified so far? You start with having n of them, then now we have all things of this sort. You might say there's 2 to the n of those, but they're not, they're multiplicities and so on, so it's really basically 4 to the n. So they're basically 4 to the n eigenvalues that you figured out for the big chain from the small chain. 4 to the n is much smaller than n factorial, right? So most of the eigenvalues for the big chain we have no idea about. It's very interesting if you do simulations or computations. take a given matrix, compute eigenvalues. You look at the eigenvalues of the small chain, then here's a list. Look at the ones for the big chain, and there are these 4 to the n over here that you can see are related to these over here. And the others seem to bear no relationship at all to the eigenvalues of the single particle chain. They just seem to be out in some other planet. But in any case, all the eigenvalues of this type for the big chain, being a sum of eigenvalues of the small chain, are at least lambda 1. And therefore, lambda 1 star is less than lambda 1. That goes to an earlier argument, but we know that all of these particular eigenvalues we found for the big chain are bigger than lambda 1, but we don't know about the others. So here we have the inequality, lambda 1 star is less than lambda 1, and of course, for all we know, there's a huge difference in one might be much smaller than the other. After all, one chain has n factorial states and n factorial eigenvalues, the other one has n for each. So here's Alice's conjecture. It's a very bold conjecture, I think. Now, you don't want to make conjectures that are easily proved false. Not good for your reputation. And he conjectured that, in fact, these were the same. So why guess this? So there was some information that came before his conjecture. So I'm sure you all know Percy-Diakhonis' name. He has this famous theorem that if you use the riffle shuffle, that 7 shuffles are enough to get close to uniform distribution. Turns out that if you take a complete graph and all the rates C sub e are 1, are constant, you can use representation theory to compute all the eigenvalues for both cases. You look at them, and the smallest eigenvalue is the same. It's not because they proved that they were the same, it's just you look at them, and they're the same. So that's a slight bit of evidence for the conjecture. And then the other result before the conjecture was that you take a star graph that has a vertex here and a bunch of edges that go out like this, that's all. If you just take a star graph and all the weights are 1 on the star graph, then the two minimal eigenvalues are the same. That's a very, very, very minimal amount of evidence for this conjecture. So then people started working on the conjecture, including me in the middle 90s. And my student Najani and her husband, Doug Rice, as I said earlier, proved that this conjecture is true for trees for arbitrary C's, arbitrary weights on the various edges. And that was the first result on any graph that had arbitrary C's. Then Chesney, we're already up to 2009, proved that it was true if, again, if the C sub E's were identity 1, if the graph is a complete multi-point graph. So got a very special kind of graph. There are other results I mentioned at the bottom here, and they weren't all special cases of conjecture. So for example, this result by Starr and Carlos. So Starr learned about this problem from me because he was a postdoc at UCLA at that time. So they did the following. They said, suppose the graph is a big piece of ZD, big finite piece, big box. So they didn't prove for the box that the two minimal critical values are the same. They found the asymptotics as n goes to infinity, as the size of the box goes to infinity, of each eigenvalue, and the asymptotics were the same. Not that the eigenvalues themselves were the same. So various results of this sort that started to complete the picture. So here's our theorem. That in fact, for any graph, finite graph, and any collection of C's, the two minimal eigenvalues are the same. So a couple of comments about why you should care. Well, if you take the number n equal 10, you want to compute the eigenvalues of 10 by 10 matrix of mathematical or something, not hard. If you take a 10 factorial by 10 factorial matrix and ask mathematically to do it, you fold up the 10 and go on. And this says they're the same. So you compute the minimal eigenvalue for the small one, you get it for the big one. The other thing that makes this interesting is that we had, in one of the slides, I had these 3 examples, and there's the one particle chain here, the chain of permutations here, then a bunch of other things in between. Once these have the same minimal eigenvalue, all these do too. So you get the result for many more changed. Okay, now I want to start saying a little bit about the proof of this conjecture, because some ideas that I think are interesting. So, going back to the result on trees by Hajani and Ugrice, the proof is inductive. You take a tree, finite tree, it has a leaf. You take that leaf and the one edge that comes out of it. If you remove it, you get a smaller tree, right? So you can try to prove that if the conjecture is true of the smaller tree, it's true of the bigger tree. Inductive argument, right? Well, if you take a general graph, and by the way, I should make sure, that argument is not trivial. Once you do the removal of the vertex and the edge, it's not immediate how to go from the smaller tree to the bigger tree. That requires work, which can be figured out. And then the first problem we had for the general problem was if you take a general graph and you want to remove a vertex together with its edges, that's going to change everything, right? So you can only do that in a way that you can hope to make a deductive argument if you modify the weights on the remaining edges in some way to compensate for the edges you've taken out. So here I have this picture thinking of this is part of the graph, and I want to remove the vertex x to get a smaller graph, one less vertex. All these I've written down, but all these edges have C's on them. And what I want to do when I take out this vertex and those four edges, I want to change the C's on the remaining edges up there in such a way that I essentially have an equivalent graph. And what do I mean by equivalent? These things look like electrical networks, right? So you can think of resistors on the edges, and there's all kinds of stuff known about electrical networks. There's inductances, which are reciprocals of resistors, and rules that say if you take a series, circuit series, and collapse it down to one resistor, how you should compute the resistor for the resulting single resistor, and similar arguments for parallel circuits. If you want to take a parallel thing and replace it by one, you replace the inductances of resistors by something or other. There's some reciprocals that come up and so on. Well, if you take the situation where you're removing, you have this one site that you want to take off, and it is connected to just two vertices. So what should you do? Well, if you think of these as being resistors, what you're doing is taking these two away and replacing it by that. That's a series reduction. And so this says whatever the C's were here, you do something to them using electrical rules to replace it by a C here. Now you already have C there. But that's a parallel reduction. You had a C here before, now you have another C, you just add it. Okay? The next case after this one is that. So this X is connected to three vertices. You want to remove this vertex and these three edges. And what you want to do, these are edges that were in the original graph. And what you want to do is figure out how to modify the C's on these edges to incorporate the effect of removing these edges. And there's a famous transformation called the star triangle transformation. How many of you heard of this? Is it famous? Somebody, people? Because it starts with a star, it's a very simple star, and replaces this by a triangle. Right? Well, you look at the two formulas you get in these two special cases, and you notice they look the same. And I'm not sure, since you know about this transformation, I've never found a reference to the next stage. So if you take one vertex here and four coming out, and you replace it by the polygon that you get instead of a triangle, there should be a star polygon transformation. I don't know if that exists in the electrical world, but anyway, we just took these two special cases, and since the answers look the same, just do it in general. And that's gives rise to the next slide here. Okay, so we're going to take this X, this vertex X, and remove it, together with all the edges it's connected to. And then we get this new smaller graph called G sub X. And you change the C's on the remaining vertices in the following way. You take, so the new C's are just, oh, let's see, there's a pointer, I forgot what it is. Yeah, that's it. here you have the new C's, they're the old C's, this is the parallel transformation here. And what you have to add, which is the contribution of the ones you've taken out, is this formula. See, that just comes from these series and star network transformations in electrical theory and blindly generalizing. You get that nice formula. So this new smaller graph with these new C's has the same electrical properties as the group. Okay, so I want to describe 4 steps in the proof. The whole proof is here. Well, and there's something right here called the octopus inequality. That's on the next slide. So forget what that is. Octopus relates to the fact that if you look at one of these things, there'll be all these tentacles that come out, right? That's the octopus inequality. So forget that for the time being. Look at the first step. First of all, the lambda 1 for the slightly smaller graph is at least as large as the one for the original graph. That's going in the right direction, since we're trying to show the lambda 1 inequality of this sort. And this uses the variational characterization. I mean, right here, oops, that. Yeah. Button is that you take a function in the variational characterization on piece of x, the smaller one, you extend it to g, take a new value at x, just make it harmonic at x. That gives you a function on g, and you just look at the variational stuff, and this inequality comes out. So the next step is to say, okay, the variational characterization gives the smallest eigenvalue as an infimum of certain things. Instead of looking at the infimum over all functions, look at it over just this class of functions. And even if you don't understand what this means right here, the point is the following, that the eigenfunctions for the chain that are not in this H generate eigenfunctions in the one particle chain. So if you know what happens to one particle chain, and you know what happens here, then you know everything. So sort of separating out the one particle chain effect from everything else. And the inequality you get is that the lambda 1 star that we cared about is the minimum for lambda 1 that we cared about, and this mu1 star. That's just from separating out these two effects. And then there's a self-constant inequality that I'll come to in a minute, but if that's true, then this mu1 star we just generated up here for G is bigger than the maximum of these things. So that's some inequality that you get from looking at this variational expression. And to complete the argument, the whole proof is here, you take u1 of G, and that's bigger than or equal to this maximum. Okay? And that's the same as that. This is the inductive assumption, right? G sub x is a smaller graph, so this is the inductive assumption. And by another one of these steps, that inequality is true. And I use 2, that, and you get the lambda 1 and lambda 1 star the same. But you got the inequality we needed. We already had one inequality, and I get the other inequality. Right? So it's not too hard. You have to know what sequence of things to do. But then we come to the octaves inequality. And I have to say that there were other groups working on this problem who got to this point, but couldn't prove the octaves inequality. So in some sense, that became the So what's this famous infamous octaves inequality? It's that. You don't need to look at it too much, but you can see the various ingredients. These are those additional rates we did, right, in removing the one vertex and its edges. These are the expressions that come up in the variational characterization of eigenvalues. And if you look at it, this is 7.24, and it's bigger than 7.24. You can interpret this as simply saying that some big matrix is positive semi-definite. Well, you can't see very well from here what it is, but I'll tell you what it is if n is equal to 3. So if n is equal to 3, this is the matrix that you want to be positive semi-definite. So you have these, so here C is these particular expressions here, D is that, you write this down. Notice that it has a certain form. So why is it that these 4 blocks are different, 2 of one type and 2 of the other type? Well, you all know that every permutation is either odd or even. And you know that when you apply a transposition, you change from odd to even or vice versa, right? And so we're in n equal 3, so there's 6 permutations. 3 of them are even and 3 of them are odd. And somehow when you go from even to even, nothing much happens. There's going to be identity there, or odd to odd. When you go from even to odd or odd to even, you get something happen. Well, so it's easy in this case to find the eigenvalues. It happens to be m 0 and 2c, each multiplicity 3. So they're all non-negative, so the matrix is positive semi-definite. Okay, so that case is easy. What you can imagine for general m, it's a mess. Okay? So let's look a little more. So here we have to check that some matrix C is positive semi-definite. Now I'm a probabilist, so there are 2 or 3 other probabilists in the audience. If you ask a probabilist, you're a statistician, some statisticians I'm sure in the audience too. You ask a probabilist or statistician, how do I check that some matrix is positive semi-definite? You don't do it by computing eigenvalues. You do it by trying to write it as a covariance matrix for some vector. It's a random vector. Every covariance matrix is positive semi-definite and vice versa. So that's what we would think about. So you try to write C. Yeah, push you wrong. Back now. Okay. Pushing, going in one direction. So you write C, Z as a random vector. Each of them has n factorial or 2 components. The reason for that is this odd even business. And so the overall, in the previous example, Z was of like 6, and now you have these 2 vectors of like 3. So remember that X has covariance matrix C times the identity. So it's clear what to do. You just take independent and then distributed random variables with variance C. So then the variance of X is right. Now, so you do that. Now how about Y? Now Y can't be independent of the X because then you would get zeros in these other 2 blocks, and that's supposed to be 0. So you can't take Y to be independent. So the natural thing, I guess it's natural, but we'll try it anyway, is to write Y as some D times X. And these 2 blocks that were oriented this way are specific things. When you take Y to be dx, that determines D. If you want to make the covariance matrix of Z be what it has to be, those 2 blocks determine D uniquely. And so you hope and pray that the Y determined this way has as its covariance matrix constant times the identity, C times the identity, right? So this is, in mathematics, the more mathematics than most of you probably, but in mathematics, their highs are their lows, right? And so you check this out for n equal to 3, and it works. For some reason, magically, the Y is right. And then you get excited, you check it for n equal to 4, and it doesn't work. So you say back to the drawing board. However, you look at n equal to 4, and it turns out that while the covariance of Y was not C times identity, it was less than or equal to in the sense of positive definiteness, as in the sense that Ci minus the covariance of Y is positive semi-definite. So, and that's enough. So what you want to do is prove that this is positive semi-definite, and then since this is, you have the right statement for the overall matrix. So you stare at this for a while, and you write this as a linear combination of matrices. The coefficients, unfortunately, in this linear combination are both positive and negative. When you're checking positive semi-definiteness, it's not good to have negative coefficients. It'll be negative. And these coefficients involve the rates, these C sub D's, but the H and J's do not. Simply just nice matrices that don't involve C's. And you have one of these matrices for each subset of the set of vertices of size 4. Now, I'll say something about why 4 and later 5 plays a special role in small. Well, you can write down what A sub J is. The entries are either 2 minus 1 to 0, depending on whether, so remember these were indexed by these permutations, and depending on whether the phi and pi prime are satisfy various properties like this, you either get 2 minus 1 to 0. But that's specific matrices. So then that reduces the problem to showing that the AJs, together with certain linear combinations, which remember had coefficients of both sides, are positive semi-definite. And for example, if you let see the linear combinations you need, you look at the D sub k, which are these particular linear combinations of the A sub j's. And those are the linear combinations that you also need to know are not negative definite for the whole group to work. Example, unequal 4. So E sub k is the k by k matrix with all 1 entries. The A matrix that we cared about, there's only one of them in this case because n is equal to 4. They're indexed by subsystem size 4. There's only one of them, and it's that. So you can compute the entry, the eigenvalues for this. So this matrix A has eigenvalues 0 and 12 with multiplicities of 10 and 2 respectively. So you go on, so that's fine. And there's no B in this case. The B's start to happen in minus 5. So now you go to n equal 5. Then this matrix B is a 60 by 60 matrix with small integer entries. So then you stare at that. How do I analyze that? Well, if you stare at it long enough, you realize that B squared is equal to square root of B. There's a lot of staring at this. Because of this, the only eigenvalues for B are 0 and 24. And it turns out their multiplicities of 4, 45, and 15. So that takes care of the case n equal 5. But we're interested in all that. Because that case n equal 5 directly by this computation. Okay, so now what about larger? So here's, you've heard of computer system proofs. That normally means that you use the computer in a proof. This is not a computer system proof. This is a real proof. However, we were never found it without the computer. So it's use it for experimentation, exploration. So let me tell you what we did to figure out. I'll tell you the punchline here. There's matrices A and B for big M. They all turn out to be block matrices, where the blocks are the A's and the B's from the n equal 4 and n equal 5 cases. And of course, you take a block matrix like this, and these are all positive semi-definite, and the whole thing is, right? Now, why would you guess that? Well, I think you wouldn't. No way to guess that. Now, to illustrate how hard this might be, we looked at a matrix of about 500 by 500. Take one of these cases where the real total matrix is 500 by 500. You're not given a matrix this way. You take in a matrix like this, and you shuffle the rows and columns in which way. So you don't see that structure. Right? It's all just a big mess. And we didn't really look for something like this. Right? We just were presented this matrix with things all over the place. They're sparse matrices, sure, but they're not organized in a very good way. So Thomas wrote down, well, there's who's better at computers than I am, wrote a little program to write this 500 by 500 roughly matrix on the screen. And you can imagine you can't get a 500 by 500 matrix on the screen. So he did it so it looks something like MapQuest or Google Maps or something. So with the cursor, you can move around. Right? You have a little piece of the matrix on the screen, and you sort of move around and try to figure out what the structure is. So then we're going to stare at it for a long time. And finally, this is good. So once you know that that's the structure of these matrices, the theorem is complete because we already know these A's, A is 5 by 4, the B is 5 by 5. Okay, well, I'll say something here about what these blocks are. You look at the various cosets or something rather than something rather than an algebraic representation of it. I won't do that. But I do want to say something about why, once you know the result for n equal to 5, you know if you're general then. That doesn't normally happen in mathematics. And the reason is the following. You have transpositions. Any transposition affects two vertices. The matrix we're looking at is something of that form. So therefore, entries of this thing in the product involve 4 vertices. There's sums of various things. But in this reduction, there was a special vertex x that was removed for the induction argument. And that gives you 5 vertices that are somehow come into any given piece of the argument, or any given piece of the matrix. And because of that, n equal 4 and 5 determines everything. And that was a surprise to us. No way of guessing that from the beginning, what the problem was. Okay, one final is this structure that I had on the graph with these Poisson processes, and when some Poisson process goes off, you do something, right? You can imagine about doing other things, other than the ones I talked about. And the question is, do all those have the same methodology, the change you can get when you do something else, whenever any of these Poisson processes fires? So here's an example, which was worked out by, again, Percy and Susan Holmes. You take perfect matchings. So you take Anthony 2K, an even number of vertices. And a matching is simply what it says. This is matched to that, that's matched to that, that's matched to that. So perfect matching is an exact pairing of the 2K points. So that's the state of the system, of matching. So what happens? Well, random times, the Poisson process corresponding to these two vertices goes off. Now, either of these two are matched in the current state of perfect matchings, in which case nothing happens, or this is matched to this thing, and this is matched to something. And what you do is you just interchange the matchings. This round right here. And that's, again, a Markov chain. State space now is a set of perfect matchings rather than permutations or subsets or things like that. And yes, the same thing is true, but it's not. So in this particular case, k equal 2 and equal 4, all of these equal to 1. It turns out the 1 is 4, and the count of 1, which is the smallest positive eigenvalue for the problem, is 6. So the corresponding result is not true. A number of people were very excited about some of these things. They worked on it very hard, and now they saw they want to do something themselves, write the paper themselves. So they were trying to figure out what generalizations there might be for this theorem. So we could take other kinds of evolutions, again, based on these Poisson processes. So here's one thing you can try. In this example I talked about, not this one, but the one I talked about mainly today, you are applying transpositions to permutation, for example. Okay? Well, how about applying permutations of size 3? Okay? At certain rates. Now you run into all kinds of problems. A transposition is its own inverse. Right? Permutation of 3 things is not. And so because it's its own inverse, it's natural to say, well, transposition and its inverse have the same rate. It's the same. But if you take a permutation of 3 things, well, it has a rate, and take some other permutation of 3 things, it has a rate, and how should those rates be related so that they're true? So there are lots of things one could try to do along these lines, and my colleague, Pietro Caputo, and a student of his who's been forgotten, have investigated this to some extent. And he, the student, I think, wrote a paper in which he tried to identify those cases that could be done in the same way, not many, those cases that were somehow trivial anyway, and all the rest. But the problem is you don't have Aldous around to give you the conjecture. So I really haven't thought about generalization very much, but if you're interested in this, what you could do is take your favorite thing you could do of this type. Do some computations of these eigenvalues. See for what choice of these rates do you get the result being true if you take small examples. And then try to prove a theorem. Okay, so this was something a little bit out of my very line of work, but it's a little fun to talk about because it doesn't involve that much probability. It's mainly linear algebra, but it's not trivial. Anybody who thinks that the undergraduate linear algebra course teaches you everything you need to know about linear algebra is wrong. Thank you very much.